This is section 3.1. We're going to be talking about complex numbers. Even though in this chapter we're supposed to be solving equations, well, we're not going to begin solving equations right off the bat. We are first going to talk a little bit about complex numbers because once we start solving equations, some of our solutions will involve complex numbers. So let's understand the answers that we're going to get first. Okay, so a complex number is a number of the form a plus bi, where a and b are real numbers. The number a is called the real part, and the number b is called the imaginary part of my complex number. So a plus bi, a is the real part of my complex number, b is the imaginary part of my complex number. They gave us a little diagram here on the kind of the structure of the types of numbers that we have. And if you notice over here, I made a weird little trippy looking little diagram on the right hand side here to sort of illustrate the types of numbers that you encounter in math classes. So let's see, let's begin with the easiest types of numbers, which are called natural numbers. The natural numbers are just 1, 2, 3, 4, 5. So positive whole numbers. They're very good for counting. That's a very simple type of set. It's a set of numbers. It's called the natural numbers. Now, there's a bigger set called the integers. The integers include 0 and include negatives. So negative 2, negative 3, negative 4, all the way to negative infinity, 0, 1, 2, 3, towards positive infinity. And notice that the natural numbers are a subset of the integers. So all natural numbers are also integers. But then there are some integers that are not natural numbers, like negative 3. The integers kind of, I guess, come about because of maybe debt. You know, you owe something to somebody. Well, now you're in the negative, I guess. I don't know. So that's so we have natural numbers, we have integers. There's an even bigger set of numbers called the rationals. The rationals are your fractions. So, but it's see, with the integers and with the natural numbers, you can sort of list them out. I mean, there's infinitely many integers, but you can sort of start listing them out. 1, 2, 3, 4, 5. You know, at least you can count them. With the rationals, counting them becomes kind of difficult. It turns out that they're actually countable. You can actually count all of the rational numbers, but in a sense, they're denser. There's more rational numbers than there are integers. And while rational numbers are fractions, where the numerator is an integer, the denominator is an integer, and well, also the denominator shouldn't be 0. And notice that all integers are also rationals. So the integers is a subset of the rational numbers. For instance, 3. 3 can just be expressed as 3 over 1. Yeah? Okay, so then you have natural numbers, integers, rationals, and then you have an even bigger set of numbers called the reals. What the heck are these reals? Turns out that the reals are the union of all rationals plus all the irrationals. So what's an irrational number? So irrational numbers are non-fractions. Non-fractions. So there are some numbers out there that cannot be expressed as a fraction. For instance, examples. An example of an irrational number would be the square root of 2. Turns out that that is an irrational number. I mean, it's a decimal, but you cannot express this decimal as a fraction. Also, the square root of 3, pi, e. You might have heard about these types of numbers. These are called irrationals. So the irrationals are decimals that cannot be expressed as a fraction. Well, then the real numbers consist of all the fractions plus all the irrationals, all those little weird numbers that cannot be expressed as fractions. It turns out that there are a lot of these irrationals out there. And then there's the even bigger set of numbers called the complex numbers. The complex numbers is what we're going to talk about in this section. So maybe it's worth your time to at least keep this hierarchy of sets of numbers in mind. So for instance, whenever somebody talks to you about a real number, now you know what they're talking about. A real number is just the set of all rationals, or all fractions, uh, together with all irrationals. So the easiest types of numbers are the natural numbers, the integers, the rationals come next, then the reals, and then the complex numbers. And turns out that there are even bigger sets of numbers. They really are not numbers anymore. At that point, they're polynomials. But in order to get into that, you gotta study more and more math. Okay, so let's talk about complex numbers right now. We're gonna be doing some arithmetic with complex numbers. So we said that a complex number is of the form a plus bi. A is called the real part, B is called the imaginary part. Okay, there is this thing called I. I has a definition. So we have that I is going to be defined as the square root of -1. Yeah, so you're just going to have to memorize it. So I is the square root of -1, and I squared. If you square I, then you end up with -1. So this is definitely something to keep in mind. So that I squared is equal to -1. You're going to be using that a lot in this section. So make sure to sort of sear that in your mind. Okay, one thing to notice here is we're going to have to play with powers of I at some point. So let's explore a little bit powers of I. So I to the first power, well, turns out it's just I. I to the second power, they told us is -1. And then I to the third, how could I possibly find I to the third? Well, one thing I could do is take advantage of exponents. I could say that I to the third is I squared times I to the first. Because then what happens is I end up adding this exponent plus this exponent. That gives me 3. And I know what I squared is -1. And I know what I is I. So this becomes negative I. I to the fourth. I could do a similar trick to figure out I to the fourth. I to the fourth is just I squared times I squared. And well, that's -1 times -1. So that becomes 1. And now I to the fifth. I to the fifth turns out is the same thing as I to the first. So I to the fifth goes back to I. I to the sixth. I to the sixth turns out is the same thing as I squared. So it's -1. And again, you could verify this using rules of exponents. Just for the sake of time, I'm just going to sort of make you aware of this. But definitely verify it by using rules of exponents, and there could be several rules of exponents that you could use to verify this. I to the seventh should be the same thing as I to the third. So that is -I. And I to the eighth should be the same thing as I to the fourth. So back to 1. And then this cycle just continues. I to the ninth is the same thing as I to the 10th is the same thing as I squared. I to the 11th is the same thing as I cubed. I to the 12th should be the same thing as I to the 4th. Notice that if the exponent happens to be a multiple of 4, so 4, 8, 12, 16, 20, 24, you're going to just end up with 1. Okay, so be aware of these powers of I. We're going to need them in a few examples here. So, okay, let's get into a little bit of arithmetic with complex numbers here. Alright, so let's begin by simplifying expressions. And well, not only simplifying them, but also using I in order to rewrite the expression. So I'll help you with the first one, and then you go ahead and try the other ones. So let's do A. So in part A, here I'm going to kind of write down the steps that are happening in between. What I notice is that this is the square root of -1 times the square root of times 7. Yeah, and so then you could almost think about this as being I times the square root of 7. Or rather, this is what I'm about to write down here is not quite right, but maybe it helps you see what's going on. So square root of negative 1 times the square root of 7. Yeah, and well, then turns out that this square root of negative 1, we had called it I, and this is square root of 7. Or you could also write square root of 7i. It doesn't matter. I'm going to always try to put the I on the right, but it doesn't matter. You could also have it on the left. So that is the simplified form of that. Now I'm using I rather than having a negative inside my square root. Okay, so pause the video. See if you can try the other 3 on your own. All right, so at this point, hopefully you have expressions for this. So let's just compare. Well, this one's just going to become, let me think about this. So negative 1 times 16. So that's the square root of negative 1, square root of 16. This is I, and this is 4. So 4i is what I'm going to conclude here. This guy right here, so let's see. So I have negative. So I gotta be careful, negative, and then I'm gonna just open a big parenthesis because this little negative out here is going to affect everything at the end. And so then I have the square root of negative 1 times 2 times 4. That's a weird looking 4. Okay. And so then I have negative, this is square root of negative 1 times the square root of 2 times the square root of 4. Okay, so that's negative. This becomes I. This is the square root of 2, and this is times 2. And then I have to apply my negative. And so then I'll just write it like this. This is going to be negative 2 root 2i. All right, so there will definitely be some simplification of radicals involved here, and so keep practice that. So last one, let's see, this is what, so this is going to become the square root of negative 1 times I'm trying to think of a perfect square that divides 48. And I think it's 16 times 3. 16 times 3, yeah. So I'm going to say 3 times 16. Again, right now I'm looking for perfect squares since I'm dealing with a square root. So this becomes the square root of negative 1, square root of 3, square root of 16. Okay, so that's I. That's the square root of 3. There's not much to do with the square root of 3. This becomes 4. So I'm going to write it like this. 4 square root of 3i. Okay. So these are my simplified forms. And I think that is it for this exercise. All right, next thing. Let's play with powers of I. Yeah? So remember, there was this little thing that we mentioned a second ago, that powers of I cycle. So maybe we can, let's see if we can answer this here. So what would be I, so yeah, let's try to simplify these expressions. I to the 11th. I to the 11th. Okay, well, I know that I to the 12th, because remember, up here we said that if the exponent, if the exponent is a multiple of 4, so for instance, if I have I to the 4th, I to the 8th, I to the 12th, I to the, what would be the next one? To the 16th, to the 20th, you're always going to end up with 1. And the exponent previous to the multiple of 4 is always going to be negative I. So that's kind of what's going on here. I know that I to the 12th, that should be 1. Yeah? And so then I to the 11th is equivalent to I to the 7th, or I to the 3rd. Yeah? Or another way to think about this is, well, let's see. You could also use some rules of exponents here, I suppose. We could say, So I mean, I know that the answer here, I'm gonna just write it down. This is supposed to be negative I. That's the correct answer. Now, how you go about it, there's several ways to go about it. You could just play with this pattern that we mentioned about, that we talked about a little bit ago, this repetition of powers of I. Or if you're comfortable with exponents, you could say that perhaps this is I to the, what is it? Let's see, 4 times I to the 4th times, so that would be 4 plus 4, that's 8, times I to the 3rd. Because that's what I to the 11th is. I to the 11th is I to the 4th times I to the 4th times I to the 3rd. Because then you have to add up all of these exponents. And I know that I to the 4th is 1 times 1, and I to the 3rd is negative I. Yeah? So that would be another way to maybe think about it, but it's up to you. Okay, the next one. What is I to the 24th? What is I to the 24th? This is the correct answer. What is I to the 24th? Well, remember what we said about this powers here. If the exponent is a multiple of 4, or rather, if the exponent is evenly divisible by 4, so 8, 12, 16, 20, 24, then so if you have I raised to an exponent that's a multiple of 4, you're going to end up with 1. Yeah? Or another way maybe to think about this, if you like to play with exponents, is to say that this is I to the 4th raised to the 6th power. Because then what happens here is the exponents multiply. 4 times 6 is 24. Yeah? That would be another way to think about this. So the correct answer here is just 1. All right, pause the video, try the other two on your own. Simplify them. All right, so let's see. Hopefully you have a simplified form of these things. Let's compare answers. So this becomes 2 to the 6th times I to the 6th. We are using a lot of rules of exponents that I haven't really explicitly talked about. I'm assuming that you have a little bit of working ability with them. So right now what happened here is that since I have multiplication, I'm multiplying 2 times I, and I'm raising that product to the 6th power. Well, that's equivalent to raising each one of the factors to the 6th power and then multiplying. Okay, well, 2 to the 6th. 2 to the 6th, so 2 times 2 times 2 times 2, 6 times. That's going to be 64. And I to the 6th, we said, well, from up here we said that I to the 6th, it turns out is negative 1, is the same thing as I squared. So times negative 1, so negative 64. That should be the correct answer there. The last one. I have negative I raised to the 74. Okay, so the first thing to notice is that I am multiplying a negative times itself an even number of times. Yeah, so a negative times itself an even number of times becomes positive. Yeah, so the result here is going to be positive. So turns out, let me just write down this intermediate step. This just becomes I to the 74. Why is that? Well, think about it like this. Negative 1 to the 2nd turns out is just 1 to the 2nd, which is 1. But negative 1 to the 3rd turns out is negative 1. Yeah, so if you have a negative and you raise it to an even power, you should always end up with something positive. If you start with a negative and you raise it to an odd power, you end up with something negative. Well, right now, negative I to the 74 turns out this becomes positive. It just becomes I to the 74. Okay, and now I gotta think, what is I to the 74? One thing I could do here, Excuse me. One thing I could do here is divide my exponent by 4. So 74 divided by 4. What is that? 74 divided by 4. It's about, what is it? It's going to be, so we said 74 divided by 4. It's about 18, 18.5. So 18 times 4, 72. So I know this. Look, I'm gonna kind of dissect here. So 74 turns out is 4 times 18 plus 2. I am sort of breaking down the exponent 74. I'm thinking about this exponent 74. Okay, so how is that going to help me? So then what I can conclude here is that this becomes I to the 4th to the 18th, and then times I squared. And notice what happened here. So what ends up happening here is you gotta multiply the exponents. And turns out that 4 times 18 is 72. Yeah? So that would be I to the 72 times I to the 2nd. And then you would have to add 72 plus 2. That would give me 74. Yeah? But now I know that I to the 4th, that's just 1. So this is like saying 1 to the 18th power. Well, that's just going to be 1 times I squared. Well, that's 1 times negative 1. So this whole thing just becomes negative 1. And there could be other ways to go about this. You might have done it differently. That's fine. If you just kind of kept this little pattern up here in mind and you just compared it and realized, oh, it's the same thing as just I squared, that's fine too. Okay, so let's continue then. Let's get into another exercise. Let's add and subtract some complex numbers. So let's finally get a little bit into the arithmetic of complex numbers. So far what we've been doing is just simplifying them, but now let's actually do some arithmetic. So pause the video, take a minute, try to simplify or perform these 3 operations, this sum, this difference, and this difference. So try to do it and express your answer. Your final answer should be in the form of a complex number, a plus bi. So yeah, please pause the video and take a minute to do this on your own. And then let's compare answers. Okay, so hopefully you have some answers now. Let's see how this goes. I'm gonna begin with the harder one, which I think is part C. I think this one's a little bit harder. Why? Because it's not in the form, my complex numbers do not involve I yet. So I have to first simplify them. So there's a few extra steps here. So let me begin with the simplifying here. So this becomes 3 plus 6i minus 2 plus 7i. So first of all, that hopefully you agree here. I had to simplify this square root of negative 36. Turns out that if you simplify the square root of negative 36, it converts into 6i. Same thing for the square root of negative 49. That's just 7i. Okay, and now I can perform the difference here. All I gotta do is real part minus real part and imaginary part minus imaginary part. Just be careful with the signs here though. So this is going to become 3 minus 2 and then plus, and then I'm gonna say 6 minus 7i. Yeah, so you don't really need this step here, but I'm just being a little kind of fastidious here, a little thorough, so that you see what's going on. I am adding the real parts or rather I'm subtracting the real parts and I am subtracting the imaginary parts. So that becomes 1 minus, you could say 1i. But 1i is just, we're just going to say I. So 1 minus I. Yeah. So I think that is our solution there for part C. 1 minus I. Okay, let's try the other ones. The other ones are a little bit more straightforward because the complex numbers were already given, I guess, in complex form. So here I'm going to say 4 minus 6, so that becomes negative 2. So I had to do this real part minus this real part. That's why I end up with negative 2. Be careful with the signs here. And now I'm going to say 5 minus negative 3. The minus negative 3, well, becomes positive 3. So really it's 5 plus 3. So that becomes plus 8i. Again, be careful with your signs. Remember that in a sense you have to distribute this negative, so this becomes negative 6 and this becomes positive 3i. Okay, so that's it for that. This last little part here, let's see. So this one's a little bit more straightforward since we're just adding. So that's 8 plus 3. So that's going to be 11. And then 6i plus 2i, well, that's 8i. Okay, so hopefully we agree on our answers, and good. Definitely pause the videos and try to do the things on your own. You're not gonna get better at it unless you practice these skills. All right, let's deal with multiplication now. Earlier I was kind of violating some rules up here when we were playing with simplifying these expressions, and you'll see what I was doing wrong here. Maybe, not that it matters, but we gotta be careful. So what ends up happening, so there's this little rule right here. This is true. This little thing here is true if A and B are positive. Yeah, so this is absolute. So if A and B happen to be positive real numbers, then the square root of the product is equal to the product of square roots. But if one of them happens to be negative, then that rule is no longer true. Yeah, so for instance here, the square root of negative 2 times the square root of negative 5, we know that we're dealing with complex numbers. Neither of these things are positive, so I have to first express them using I, and then when I actually successfully express this expression using I, then I end up with I squared, which becomes negative 1. So this product here becomes negative square root of 10. If we didn't know any better though, we would have said square root of negative 2 times square root of negative 5 is equal to the square root of negative 2 times negative 5. But this is incorrect. This is very wrong. So keep that in mind. You can use this rule here, the square root of A times the square root of B equals the square root of A times B, only if A and B are positive. And well, if you notice up here earlier, I was kind of violating that rule. I was saying that the square root of negative 1 times 7 equals the square root of negative 1 times the square root of 7. That's not quite true there. But that's okay. If you know the rules, then I guess maybe you bend them a little bit sometimes, and as long as you know what the end game is supposed to be. Okay, so let's see. Let's multiply some complex numbers. All right, so you have 4 multiplications to perform here. Pause the video and try to multiply them. And not only that, I guess the instructions should say here, multiply and express solution. Express the solution and form A plus BI. Okay, yeah, pause the video, try to perform this 4 multiplications. Okay, so hopefully you have answers, and your answers are in the form a plus bi. Let's compare answers. All right, so I'm gonna say, first let me simplify these things. So this becomes square root of 2i times square root of 5i, okay? And so then this becomes square root of 2 times square root of 5 times I squared. And so then this becomes square root of 10. And this is possible now. Why? Because remember we said that we can apply this little rule. Why? Because this guy's positive and this guy's positive. So this is actually valid now. And I know that I squared is negative 1. So times negative 1. So I'm going to say negative square root of 10. That is the multiplication. But then I asked you to express the solution in the form a plus bi. Yeah, so I guess what I need to do here is, turns out that this is the real part of my complex number. This is the a. What about the b though? I don't see any I involved here. Well, we could write it like this. Negative 10 plus 0i. So now I have it in the complex form. It's a little redundant. I mean, nobody writes plus 0, but the reason why I'm asking you to express your solution in this form is because perhaps if you're doing homework in my math lab might require you to enter the solution as a complex number. Not sure though. Okay, let's do the next multiplication. Okay, so for the next multiplication, I gotta think FOIL. I gotta think multiplication of a binomial times another binomial. So I'm gonna do 1 times 1 and 1 times 3i. So that becomes 1 plus 3i. Then I'm gonna do 2i times 1, so plus 2i, and 2i times 3i. That's 6i squared. And now I gotta simplify and collect like terms. So this becomes 1 plus 5i, and then minus 6. How did I get this minus 6? Well, you gotta remember that I squared is negative 1. So it's 6 times negative 1. Well, that's negative 6. And now I gotta collect like terms. 1 minus 6, I guess that's negative 5, plus 5i. I would say that that is the simplified form of my second multiplication. Okay, let's try the third one. So this means 3 minus 7i times 3 minus 7i. So similar as the previous one, this is going to become 9 minus 21i minus 21i, 21i, plus 49i squared. So here what happened, it was 3 times 3, well that's how I got this 9, 3 times negative 7i, that's negative 21i, negative 7 times 3i, that's negative 21i, negative 7i times negative 7i, that's positive 49i squared. Collect like terms and simplify now. So 9 minus 42i minus 49. Okay, so let me finish this. So negative 40 minus 42i is my final answer. Okay, let's try the last one. Here, this little square root got a little too crazy and took over this parentheses, but this square root is just supposed to only apply to negative 81. So let me rewrite this using I. So this becomes 1 plus 2i times 2 minus 9i. And now I can multiply this in the same fashion that I've been multiplying the other ones. So this is going to become 2, because I gotta do 1 times 2, and then 1 times negative 9i, that becomes negative 9i, and then 2i times 2, that's 4i, and then 2i times negative 9i, that's going to become negative 18i squared. And you gotta keep in mind that I squared is negative 1. So let's simplify and collect like terms. So this becomes 2 minus, so that becomes minus 5i, and then this should become plus 18. So that's 20 minus 5i. Okay, so hopefully we agree on the answers for these products. And so we have talked so far about what? Powers of I, addition, subtraction of complex numbers, multiplication of complex numbers, and I guess the last thing we gotta talk about is division of complex numbers. But before we can talk about division of complex numbers, we gotta talk about what's called the conjugate of a complex number. So the conjugate of a complex number. So if you give me a complex number a plus bi, so you gave me some complex number a plus bi, its conjugate is a minus bi. They are called complex conjugates. So there's these two complex numbers. All the difference between these two complex numbers is that the imaginary parts have opposite signs. The real parts are identical. The imaginary parts just have opposite signs. If this guy's negative, this one's positive. If this guy's positive, the other one has a negative imaginary part. And why are they called conjugate complex numbers? Because later on, whenever we are actually solving equations, you'll notice that any time that you have complex number solutions to an equation, the complex number solutions always come in pairs, in conjugate pairs. So if 3 minus I was a solution to some equation that you were trying to solve, then 3 plus I is also a solution. That's kind of strange. Why is that? Why is it that if you have a complex number solution, its conjugate also has to be a solution to the equation? Weird things that keep you up at night, huh? Okay, so for instance here they give us some examples. You have negative 3 plus 7i, its conjugate would be negative 3 minus 7i. 14 minus 5i, its conjugate would be 14 plus 5i. What's the conjugate of 8i? Well, negative 8i. It turns out that another kind of neat and useful things about complex numbers and the conjugates, well, conjugates of complex numbers, is that if you multiply a complex number times its conjugate, the result should just be a real number. Okay, so let's see. Let's before we do some division of complex numbers, which is the last thing in this section, let's just find the complex conjugates and multiply by the complex conjugate. So here in this particular example, I would have 2 minus 3i. So 2 plus 3i and 2 minus 3i, those are complex conjugates. And now what happens if I multiply these two complex numbers? Well, I end up with this 4 minus 6i plus 6i minus 9i squared. That's what happens if I multiply this complex number times that complex number. Now let me simplify and collect like terms. Well, negative 6i plus 6i, that's gone. So this becomes 4 plus 9, and that's 13. So notice that if I multiplied a complex number times its conjugate, I end up with a real number. I should not have an I anymore. Okay, so then let's try the next one. That's the complex conjugate of this number, or this is the conjugate of this complex number. Now let's multiply. So this becomes 16 plus 4i minus 4i minus I squared, and the middle terms cancel. This just becomes 16 plus 1, so that's 17. So anytime that you multiply a complex number times its conjugate, the result is a real number. That's useful. That's what's going to help us divide complex numbers. Alright, so let's divide some complex numbers, and that'll be it for this section. The idea with dividing by complex numbers, you might have heard about rationalizing denominators. You do not want to have radicals, square roots in the denominator. So you might have learned in the past about rationalizing denominators. Well, that's kind of what's going on here. Because remember, I is the square root of -1. So technically I have a complex, I have a radical, I have a square root in the denominator. So I gotta get rid of it because I want to rationalize the denominator. And that is kind of what we're doing when we divide complex numbers. So always multiply the numerator and the denominator by the conjugate of the denominator. That's what we gotta do. We gotta multiply the fraction both on top and the bottom by the conjugate of the denominator. What we're really doing is just rationalizing fractions. All right, so I'll help you with the first one and you try the other two on your own. So I'm going to have to multiply by 3 minus I and by 3 minus I. That's the conjugate of the denominator. So my denominator was 3 plus I, its conjugate is 3 minus I, and now I just gotta multiply. Okay, so maybe one thing that we should notice here is that let's see. So if you have, just to make multiplication a little bit easier, if you have a plus bi times a minus bi, so if I'm multiplying a complex number times its conjugate, I end up with a squared plus b squared. Yeah, that's sort of something to conclude from these examples here. So then let's think about what's going to happen here. This is just going to become 3 squared plus 1 squared. And then in the numerator, I'm going to have 6 minus 2i. So that becomes 6 minus 2i divided by 4. Okay? And then I'm going to say this is 6 over 4 minus 2 over 4i. Alright, let me simplify that even further. So that becomes 3 halves minus 1 half I. And I think that is my division. So I am writing the division as a complex number. So 3 halves is my real part, -1 half is my imaginary part. Okay, pause the video. Try to perform the other two divisions on your own. Okay, so hopefully you got a chance to give these other two divisions, just work on them. Let's compare answers. So this becomes 4 minus 3i. I gotta multiply by the conjugate of the denominator times 4 minus 3i. So I know that my denominator is just going to become 16 plus 9. Yeah, this is going to be 4 times 4, and then 3i times -3i, that's going to be -9i squared. Well, that's going to become +9. And my numerator is a little bit more complicated. I guess that's 20 minus 15i minus 12i plus 9. No, minus 9. So plus 9i squared, I'm going to say plus 9i squared. Okay, so that becomes 20. The I squared, you got to remember, I squared is -1, so that's like saying 20 minus 9. So 20 minus 9 is 11. And then -15 minus 12, that's going to become -27. and my denominator is 25. Okay? And now I'm just going to break up this fraction and write it like this: 11 over 25 minus 27 over 25i. That is the answer that I want to get, because I want to write my answer as a complex number as well. Last one. Let's see. So I gotta multiply both numerator and the denominator by the conjugate of the denominator. So by 5 plus 4i. 5 plus 4i. And that's going to become 25. 25 plus 16. That's my denominator. Now in my numerator is going to be a little bit messier. That's okay. Let's see. So my numerator is going to be 10. 10 plus 8i plus 5 square root of 3i plus 4 square root of 3i squared. That's what I get in the numerator. So 2 times 5, 2 times 4i, square root of 3 times 5i, square root of 3i times 4i. Okay, so let's see. This is going to be, my numerator is just what, 41? So 16 plus 25, so 41. And my numerator, it's going to be weird. So my numerator is this. So then look, I squared becomes -1. So this whole part right here becomes negative. So then I'm going to have 10 minus 4 square root of 3. That's the real part. And now the imaginary part, I'm going to say plus 8 plus 5 square root of 3 I, all of this divided by 41. This is messy. This is very messy. So the real part is 10 plus 4 minus 4 square root of 3. And the imaginary part is 8 plus 5 square root of 3. And I don't really want to use decimals, so I'm just going to leave it like this, which is going to be kind of ugly, but it is what it is. So then this becomes 10 minus 4 square root of 3 over 41 plus 8 plus 5 square root of 3 over 41i. That one was messy. This one's messy. And yeah, we don't really need to use a calculator here. You could just leave your answers like this. Although entering this into my math lab would not be fun. But I don't think you have to do anything like that. Okay, so that's it for this section. In the next sections, we'll actually get on with solving equations. Okay, thank you.